Hello and welcome to this video. In this video, we will study 18th set of problems on complex numbers, that is problem number 171 to 180. So as I always say in my videos that you should pause the video when I'm reading the problem, and if you cannot solve the problem yourself, then look at the solution. So without further ado, let's get started. Problem 171 says that if n is greater than 1, show that the roots of equation z to the power n is equal to 1 plus z to the power n are collinear. So we are given that z to the power n is equal to z plus 1 to the power n. That means mod of z to the power n is equal to mod of z plus 1 to the power n, which basically means mod of z is equal to mod of z plus 1. So mod of z when squared it will be x square, and mod of z plus 1 when squared it will be x square plus 2x plus 1, because y square will cancel out on both sides, and then we can cancel out x square. So what will remain is 2x plus 1, which is the equation of a straight line on which all the roots of the given equation will lie. That's how we prove that all the points are collinear. Problem 172 says that if A, B, C, and D are four complex numbers, then show that AD into BC is less than equal to BD into CA plus CD into AB. So to solve this problem, we assume that Z1, Z2, Z3, and Z4 represent points A, B, C, and D. Then AD will become mod of Z1 minus Z4, and BC will become mod of Z2 minus Z3. Then we let A is equal to Z1 minus Z4 into Z2 minus Z3, B is equal to Z2 minus Z4 into Z3 minus Z1, and C is Z3 minus Z4 into Z1 minus Z2. Now we evaluate B plus C, which will be equal to, on simplification, equal to minus A. So we can say that mod of A is equal to mod of B plus C, which is less than equal to mod of B plus mod of C. So that essentially implies that this equation is true, which is basic. This should be less than equal to. This should not be equal to, which basically means AD into BC is less than equal to BD into CA plus CD into AB, because Z1 minus Z4 would be AD, Z2 minus Z3 would be BC, Z2 minus Z4 would be BD, Z3 minus Z1 would be CA, Z3 minus Z4 would be CD, and Z1 minus Z2 would be AB. That's how we have arrived at this equation. Problem 173 says that if AB belongs to real set and both are not 0, then show that the equation of line joining A and IB is 1 by 2A minus I by 2B into Z plus 1 by 2A plus I by 2B Z bar is equal to 1. So we know that equation of a line passing through two complex numbers is given by Z bar by the determinant Z bar 1 and Z1 bar 1 and Z2 bar 1. So in this case, it would be IB bar, which is equal to minus I without bar and B. This is a typing mistake. So when we evaluate this equation, we get the formula, get the equation as A bar plus IB bar minus A minus B into Z bar. There should be Z here. This should be with Z. Okay. Minus I into AB bar plus A bar B is equal to 0. That is A plus IB into Z minus A minus B Z bar minus 2ABI. So this we can write as, now you see that this is equal to 0 because A is equal to A bar and B is equal to B bar, because both are real. That's how we have come to this equation. Now once we have this equation, it is repeated actually, not repeated, we take 2AB to the right hand side and then we divide both sides by 2ABI. So when this will be divided by 2ABI, it will become minus I by 2B, and IB will become 1 by 2A. So 1 by 2A minus I by 2B into Z, plus when this will be divided by 2AIB, it would be minus of 1 by 2A. When this gets multiplied with this minus, it will become plus 1 by 2A. And similarly, the other would be I by 2B into Z bar is equal to 1. Problem 174 says that if Z1 and Z2 are two complex numbers such that mod of Z1 minus mod of Z2 is equal to mod of Z1 minus Z2, then show that arg of Z1 minus arg of Z2 is equal to 2 and pi, where n is in the set of integers. So we let Z1 is equal to R1 E theta 1 and R2 is equal to E I theta 2. So from this we see that R1 minus R2 would be square root of, this is the modulus, that's why it would be square root of Z1 minus Z2 whole square. So we get here R1 minus cos theta 1 minus R2 cos theta 2 whole square plus R1 sin theta 1 minus R2 sin theta 2 whole square. Now we square both sides and cancel out R1 square and R2 square. We find that 2R1 R2 is equal to 2R1 R2 cos theta 1 minus theta 2. Now we cancel out 2R1 R2 as well. We get cos theta 1 minus cos theta 2 is equal to cos 2n pi, because this will become 1, which is equal to 2n pi. So we can say that argument of Z1 minus Z2 is 2n pi. Problem 175 says that let A, B, C, D, E be points in the complex plane representing complex numbers Z1, Z2, Z3, Z4, Z5 respectively. If Z3 minus Z4 into Z3 minus Z2 into Z4 is equal to Z1 minus Z2 into Z5, prove that triangle ABC and DOE are similar. So the triangles would be similar if the ratio of their sides are equal and one of the angles is equal. So we have this modulus equation, and this is the argument equation, which essentially means Z3 minus Z1 divided by Z2 minus Z1 is equal to Z5 minus Z4 by minus Z4. So when you solve this equation, you will arrive at the given equality, and hence the triangles are similar. Sorry, it was not congruency, this was similarity problem. Let Z and Z0 are two complex numbers, and Z0 bar, comma 1 are represented by points P, P0, Q and A respectively. If mod Z is equal to 1, show that the triangle POP0 and AOQ are congruent, and hence mod of Z minus Z0 is equal to mod of Z0 bar minus 1, where O represents the origin. So we are given that O is equal to 1 and mod Z is equal to 1. So mod Z is OP, which implies OA is equal to OP. Now OP0 is equal to mod of Z0 and OQ is equal to mod of Z0 bar, which will be equal to mod of Z into mod of Z0 bar. But we have that Z mod is equal to 1 here. So we substitute in this equation, we get this equal to mod of Z0. So we see that OP0 and OQ are also 1. Now we are given that P0 OP is equal to R Z0 by Z. Okay. So yeah, this is given. Now we take angle AOQ. Okay, angle AOQ will be argument of 1 by Z0 bar, which will be equal to argument Z bar by Z0 bar, because Z bar is equal to 1. So this one, if we substitute by Z bar, Z will cancel out and Z bar will be there. Now this whole thing is equal to minus of argument Z0 bar by Z bar. We reverse the arguments, and this will be equal to minus R bar over Z0 by Z, which will be equal to argument Z0 by Z. We remove the bar and minus sign, which is equal to P0 OP, and thus the triangles are congruent because two sides are equal and one angle is equal. Problem 177 says that if the line segment joining Z1 and Z2 is divided by P and Q in the ratio A is to B, this should be B, not N. Internally and externally, then find OP square plus OQ square, where O is origin. So P would be AZ2 plus BZ1 by A plus B. Q would be AZ2 minus BZ1 by A minus B. This comes from the intersection formula. Once we have that, we can evaluate OP square, which is equal to, you can read out the equations and you can figure out this is equal to 1 by A square plus B square multiplied with A square mod Z2 square plus B square mod Z1 square plus AB Z2 bar plus Z1 bar Z2. And similarly, you can find OQ square, and that is left as an exercise for you. And once you have found OQ square, you can add them and find the sum. Problem 178 says that let Z1, Z2, Z3 be three complex numbers, A, B, C be real numbers, not all zero, such that A plus B plus C is equal to 0, and A, Z1, B, Z2 plus C, Z3 is equal to 0, then show that Z1, Z2, Z3 are collinear. So C is not equal to 0, and A plus B plus C is equal to 0, so C is equal to minus A plus B. Now once it is this much, we can substitute in the equation AZ1 plus BZ2 plus CZ3 is equal to 0. So it becomes AZ1 plus BZ2 minus A plus BZ3 is equal to 0. That means Z3 is equal to AZ1 plus BZ2 by A plus B. So from intersection formula, we know that this represents the line segment division in the ratio A is to B. And that's why Z1, Z2, Z3 will be all collinear. Problem 179 says that if Z1 plus Z2 plus up to Zn is equal to 0, prove that if a line passes through origin, then all these do not lie on the same side of the line provided they provided they do not lie on the same line. So we let equation of a line passing through origin a z bar plus a bar z is equal to 0. Let's assume that all the points lie on the one side of origin. Now, since this line is passing through origin, the constant plus b, which we have in a typical line of equation of a line, that b will become 0 because that b represents the intercept on y-axis. But for a line passing through origin, intercept would be 0. So the equation of line is a z bar plus a bar z is equal to 0. Now, since all the points lie on one particular side of this line, we have a z I bar plus a bar z I will be greater than 0 or less than 0 because lines are all on one side. So from this, we can say that a sum of I is equal to 1 to n z I bar plus a bar sum from I to n z I is all greater than 0 or less than 0. But we are given that summation of z I is equal to 0 and summation of z I bar is equal to 0. Because if summation of z I is 0, summation of z bar will also be equal to 0. From this, we see that this sigma over z I and z I bar over 1 to n would be 0. But from our assumption, we found that it is either greater than 0 or less than 0. That's why we have contradiction in our assumption and the result. So all the points cannot lie on the same side of line. Problem 180 says that the points z1 is equal to 9 plus 12i and z2 is equal to 6 minus 8i are given on a complex plane. Find the equation of angle found by the vector representing z1 and z2. So we let OA and OB be the unit vectors representing z1 and z2. So unit vector are given by OA is equal to z1 by z1 bar and OB is equal to z2 by z2 bar. Sorry, mod z2 and mod z1. So now the equation of bisector from vector algebra we get as z prime, we can assume z prime is equal to z1 by mod z1 plus z2 by mod z2. So this would be unit vector of bisector, but to make that a vector without having unit vector, a general vector, we have to multiply it with t, where t is some arbitrary positive integer so that it can have any length. So that would be z is equal to t into z1 by mod z1 plus z2 by mod z2 is equal to 6 by 5t. We get 6 by 5 on substitution of value of z1, z2 and mod z1, mod z2. So with this, we come to the end of 18th set of problems on complex numbers. If you have found the video useful and informative, then please subscribe to the channel and like the video. And if you have a comment or a suggestion or you want to say something to me, then please make use of the comment box. And do not forget to press the bell icon when you subscribe to the channel so that you can get notification of new videos. And do not forget to like and share as much as you can so that other students like you can benefit from this video. Thanks a lot for watching. Enjoy.